Now, it wouldn't be physics without having us do a little bit of graphical analysis. So the equation for work that we got, assuming that, F and D are kind of pointing in the same direction, that W equals FD, of course it has a catch to it, like everything we learned in physics. So the catch is that the force has to be constant. What are we going to do if that force changes? Well, I love calculus. That's what I would use. Calculus is not going to be an option for a Physics 20 student, so we're going to do the next best thing. If the force is changing and we would like to find the work done, we are going to look at the area between the curve and the displacement, or the x-axis, on this force displacement graph. So we're kind of doing things that we did in kinematics. So like, for example, if you had a velocity time graph and wanted to find the displacement, you took the area between the velocity curve and the time axis. That's what we're exactly going to do here. So we're going to have these force displacement graphs. You may see them called force position graphs. Basically, you're going to take the area between the curve itself and the x-axis. Anything above the x-axis is positive work. Anything below the x-axis is negative work. So we're going to just do a couple of examples with this. So we want to find the work done to move an object 4 meters by the force represented in the graph below. Right, so in this graph below, we only want to find the work done up to 4 meters. So we're only looking for the area between this curve and our x-axis, our displacement. So the work is just going to be equal to the area. Now we have a triangle. We know that the area of a triangle is just half base times height. So this triangle, it has a base of 4 meters, and then it has a height of 100 newtons. Or 100.0 newtons, I guess, if I want to respect the digits. So I got 100 times 4 divided by 2. So this is going to give me a work of about 200 joules. For the moment, don't worry too much about significant digits. On an exam or something, I would tell you, give your answer to so many significant digits. So we're going to find that in this case, with the force changing, the work done on this object is about 200 joules. And like I said, we try to keep the shape simple. A triangle is very simple. The only thing we might do to complicate it a little more is give you something that looks like this. So we'd like to determine the work done to move an object 30 meters by the force on the object represented in the graph below. Right, once again, in this case, the work is going to be equal to the area. Well, this time we have two areas. So I kind of have this first piece here, which I'll call A1. So I have that rectangle. And then I have this teeny tiny triangle on the end here. I'll call that A2. So we can say that this is A1 plus A2. Well, A1 being a rectangle, we'll just do the length times the width. So this is going to have a length of 20 meters, and it's going to have a width of 100 newtons. So 100 times 20, we're going to get 2,000 joules, because newton times a meter is going to give us joules. The second area, we have a triangle. We're going to do half base times height. So the base of this triangle, keep in mind it starts at 20 and goes to 30. So it's going to have a base of 10 meters, and then this is going to have a height of 100 newtons. So this is going to give me an area of about 500 joules. Again, newton times meter gives us a joule. So last thing, let's put the two together. So the total work is going to be the two areas. So we get 2,000 joules plus 500 joules. So the work done on this object is going to be about 2,500 joules, or 2.5 kilojoules. Again, don't worry about significant digits for this question. On an exam, I'd say probably something along the lines of give your answer to so many significant digits. But yeah, if you have a force that's not constant and you're given an FD graph, calculate the area between the curve and the x-axis. That'll give you your work done.